Hello everyone, I welcome you all to the course of heat transfer. Today we will discuss a couple of problems on convection. The first problem goes like this. An engine oil at 60 degrees Celsius flows over a 5 meter long flat plate whose temperature is 20 degrees Celsius with a velocity of 2 meters per second. Determine the total drag force and the rate of heat transfer per unit width of the entire plate. Now, if you look at the diagram, you have a plate, flat plate. The length is 5 meter and he has given per unit width. So you can consider the width of the plate to be 1 meter. And in this case, the plate is at 20 degrees Celsius. Over this plate, they are passing a hot oil which is at 60 degrees Celsius. In comparison to the temperature of plate, the temperature of oil is higher, hence heat will transfer from oil to the plate. So that is why the symbol is given, Q will get into the plate because the temperature of the surface of the plate is lower than that of the flowing fluid. In this case, the fluid is engine oil. Now you are asked to calculate total drag force as well as the rate of heat transfer per unit width of the plate. Now, before we begin, first we need to understand whether the flow is laminar or turbulent. We have already discussed for a flat plate, if the Reynolds number is greater than 5 into 10 to the power 5, it is turbulent, and if it is less than 5 into 10 to the power 5, it is laminar. Now that can be determined using Reynolds number with the formula of VL upon mu or rho VL upon mu, where mu is the kinematic viscosity. If I replace this mu by rho, so rho will be in the numerator, rho VL upon mu, where mu is the dynamic viscosity. Now we don't know the value of the kinematic viscosity or the dynamic viscosity, or it could be the density. Now that will be taken from heat transfer data handbook at the fill temperature. Now the fill temperature is nothing but the average temperature of surface as well as the flowing fluid. The surface is at 20 degrees Celsius and the fluid is at 60 degrees Celsius. If you take the average, your fill temperature will be 40 degrees Celsius. Therefore, you need to take the properties corresponding to 40 degrees Celsius. Now, how to refer to the heat transfer data handbook? I'm telling you, I'm referring to the 8th edition of heat and mass transfer data handbook. If you open up the contents, you will have property values. So in this case, we need to get the values for the fluid, which is oil. So it will fall under the category of liquids. So if you go by the page number, it is in the page 22. Now, if you look at the page number 22, you have property values of liquids in saturated state. The first liquid is carbon dioxide, glycerin, sulfur dioxide, and the list goes on. At the end, you have engine oil unused. So this is what we need to refer to. Now, under engine oil in page number 25 of 8th edition, if you go by the temperatures corresponding to 40 degrees Celsius, you have density value as 876 kg per meter cube, thermal conductivity 0.144 watt per meter Kelvin, Prandtl number 2870, kinematic viscosity 241 into 10 raised to minus 6. In this case, it is 242. A little variation is acceptable. At the same time, you can also have the values of thermal diffusivity, specific heat. All these values can be obtained from the tables. So using the values, if you calculate the Reynolds number is V into L upon kinematic viscosity, where V is the velocity. You substitute the values, you will have a Reynolds number 4.13 to 10 to the power 4. Now, obviously, this is less than 5 into 10 to the power 5. Hence, we can conclude that the flow is laminar. Next, in order to calculate the drag force, we have formula drag force FD is equals to CF into A into rho V square from 2. Now again, if you go by the contents, you have post convection back to external flow in page number 113. Now here, the equation for CF is given, which is 1.328 into RE to the power minus 0.5. I'm giving you the reference. It is in page number 113, equation 1.0, where CFL is nothing but average friction coefficient up to the distance L from the leading edge. Now, if you calculate the value of CF or CFL, you'll get 0.00653. Put the RE value as 4.13 to 10 to the power 4. 4 to the power minus 0.5 is nothing but you can divide the root of this to 1.328. One and the same. Once you get the value of CF, you can put in the equation of FD is equals to CF into A into rho V square upon 2. Here area is nothing but as specified length into width. The length of the plate is being 5 meter and width is 1 meter. And the density value you have taken out as 876 and the velocity is being 2 meter per second. If you substitute the values, you'll end up with a drag force as 57.2 meter. Coming to the second part of the question, wherein you need to calculate the heat transfer. In order to calculate heat transfer, you need to know the value of H, which is coefficient of convective coefficient or coefficient of heat transfer. It is given by Nusselt number is equals to HL upon K, where K is thermal conductivity of the fluid. Now L you know, which is 5 meter. The only unknown will be H. But Nusselt number is calculated using the empirical relation. Again, from the heat transfer data handbook, equation 1.1, the local Nusselt number is given by 0.332 Re to the power 0.5 into quantum number to the power 0.33 or 1 by 3. Now the average Nusselt number is 2 times of local Nusselt number, which is given in equation 1.3 on page number 140. And using that, if you substitute the value, the Nusselt number is equal to 0. So here is a mistake. There should be a point here. It is 0.664 Re to the power 1 by 2 into quantum number to the power 1 by 3. We have calculated Reynolds number. We have noted down the value of quantum number from the data handbook. If you substitute, you will get a Nusselt number 1980. So this is average Nusselt number. In equation 1.1, he has given local Nusselt number. The average Nusselt number is 2 times of local Nusselt number. Please understand this. Now, once you know the value of Nusselt number, you can equate it to HL upon K, where K is known to you, which is 0.144 and L is 5 meter. If you substitute, you will get H value as 55.2 watt per meter per Kelvin. The next step is to calculate heat transfer using the Newton's law of cooling. You can calculate Q is equal to HA into T infinity minus Ts. Here T infinity is higher compared to the Ts. Generally it will be Ts minus T infinity. In this case, heat is transferred to the plate. Hence it is T infinity minus Ts. If you substitute the value of H as 55.2 and A as 5 meter into 1 meter, so that is 5 meters square, and the difference in temperature is substituted as 40, which is 60 minus 20. We'll end up with the value 11,040 watts. Let us consider one more interesting problem. The decorative plastic film on a copper sphere of 10 mm diameter is cured in an oven at 75 degrees Celsius. Upon removal from the oven, the sphere is subjected to an air stream, which is at 1 atmospheric pressure and 23 degrees Celsius, having the velocity of 10 meters per second. Estimate how long it will take to cool the sphere to 35 degrees Celsius. Now, this problem is very interesting because it includes convection at the same time unsteady state. First, let us understand the problem. You have a copper sphere. It is having a diameter of 10 mm and it is wrapped with a plastic film and it is placed in an oven. The temperature being 75 degrees Celsius. Once you remove the sphere along with the wrapped plastic film, we are expecting the plastic film to adhere to the surface of the sphere. Now, in order to cool that, we are exposing the sphere to atmospheric pressure, which is 1 atmospheric pressure, and the air is at 23 degrees Celsius, and the air is flowing at 10 meters per second. We need to calculate the time taken by the sphere to cool from 75 degrees Celsius to 35 degrees Celsius for a given condition. The given conditions are the atmospheric pressure is 1 atmospheric pressure and you are placing the sphere in a stream of air which is at 23 degrees Celsius and air is flowing at 10 meters per second. So this is the problem that you need to solve. Now this can be done with some assumptions, that is negligible thermal resistance for the plastic layer and the sphere is isothermal spatially and the radiation is neglected. Now, in order to solve, we will use the equation the temperature distribution is equal to e to the power minus HA upon rho CV into T, which we have discussed earlier. The temperature distribution is being T minus T infinity upon Ti minus T. Now we need to know the value of density, specific heat for the sphere material, which is copper. In order to know the values, again you need to refer to the data handbook. If you open the contents, first you have property values. In that you can go with the metals. So you have a list starting from aluminum, pure aluminum alloy, and the list goes on with brass, bronze, carbon steel, etc. Now in page number 2, you have copper, pure. You can have the values of density, thermal diffusivity, specific heat, as well as thermal conductivity. Now, if you go by the value in page number 2 for copper, the value of density is 8954. The value of specific heat is 383, and the value of thermal conductivity is 386. Now, with little variation, these values are taken. There could be pure copper, there could be some alloy. Little variation is acceptable. Now you've got the properties of copper. At the same time, you also need to know the values of or the properties of air. In that case, you need to go with the property values of gases and vapors, which will start at page number 34 in 8th edition. Now, if you open the page number 54, you have property values of gases at 1 atmospheric pressure. Now, it is dry air. You have temperature ranging from -150 up to 1200 degrees Celsius. You can have the value of density, dynamic viscosity, kinematic viscosity, thermal diffusivity, Prandtl number, specific heat, thermal conductivity. If you take the values of air, which is at 23 degrees Celsius, now you have the values for 20 degrees Celsius as well as 30 degrees Celsius. You need to take a linear interpolation and get the value of properties corresponding to temperature 20. Now this temperature should be 348. There is a small correction, make that. Once you get the values by taking the interpolation, because all the time you will not get the exact temperature in the data handbook. You may also be required to take linear interpolation for some values. Once you get the property values, you can substitute in rho v Cp h into A. Tau will be here. It is same expression that we have seen. T minus T infinity upon Ti minus T infinity is equals to e to the power minus Ha upon rho Cv into T, which is an unsteady state. Now here we don't know the value of H. Now how to calculate that? Again, we should refer to the empirical relations for Nusselt number. I'm giving you the reference for this equation. You can find this under flow over spheres. As it is a sphere, we should consider flow over spheres. It is in page number 120 and equation 3.2. If you look into it, the Nusselt number is given by E plus 0.4 multiplied by Re to the power 1 by 2 plus 0.06 Re to the power 0.67 or 2 by 3. This whole bracket is multiplied by 0.4 power of Prandtl number multiplied by mu infinity upon mu s. Now here we got two values for mu. One is mu infinity and the one is mu s. The difference is being mu infinity is nothing but the dynamic viscosity corresponding to fluid temperature, whereas μs corresponds to dynamic viscosity corresponding to surface temperature. Now, if you substitute the values, you'll get the Nusselt number as 47.4. Again, Nusselt number, if you equate it to HD by K, in case of flat plate, we took the dimensional parameter to be length. In case of sphere, the dimensional length will be diameter. HD by K will have the value of H as 122 watt per meter square Kelvin. And once you know the value of H, it is easy to substitute in this equation. Now here, generally we used to take Ti minus T infinity in the denominator, but here it is appearing in the numerator because it is equated to e to the power minus HA upon rho CV. So that has been compensated by taking the reciprocal. The minus sign has been taken out. That is simple mathematics to know that. So if you solve for the time, you'll end up with a value 69.2 seconds. Next class, we will discuss some more problems related to convection, boundary layer, etc. With this, I will stop. Thank you.